I want to make sure that we understand what the p-value means. I think it's quite critical. And I've said this in the previous slide that the p-value is that probability of getting that sample mean or sample proportion when you expected the population mean or respective population proportion. So in the previous example, the p-value was 0.0087 or less than 1/10 of 1%. This is much less than our alpha of 0.05, so we reject the null hypothesis. This is the same as finding that our t-stat is 3.94, which is greater than our t-critical. Again, this simply means that the true mean attitude is significantly different than 3. We still need to check that the sample mean is higher than 3, but we can see that 3.75 is greater than 3, so that's why we would reject the null hypothesis and say that the evidence does support the claim. So what does this p-value mean? Well, the precise definition will be explained more in the next example. It is the probability that we would get a sample mean of 3.75, which is different from the assumed 3.0 due to sampling error, when the population mean is actually 3. In a sloppy way, that is easier to remember. This is the probability that a result is due to sampling error. This idea of sampling error is quite important. Let's assume a normal distribution. We draw our confidence intervals, which say that if we split our alpha, that on the right-hand side, alpha divided by 2, alpha divided by 2. We would see natural variations around our mean. And anywhere between our right and left or upper limit and our lower limit, we'd say that these variations are just due to sampling error. When we get a result that is either more or less than that t-critical or that alpha, then we would say that this is due to something other than sampling error, and we don't try to define it, we just say that it's non-sampling error. So it could either be more than or less than. Let me provide a coin toss example. Let's say that I were to take a fair coin and I flipped it and I got 6 out of 10 heads. Well, you'd think, could that happen? Sure, it could happen. In fact, we can use what's called a binomial distribution, and we could say, what's the probability of getting more than 6 out of 10 heads? Or what's the probability of getting 6 heads or more when we flip the coin 10 times? We find that that is approximately equal to 17%. That's not too surprising. If we increase this tenfold and we said, okay, we're going to flip this coin 100 times, and we get the same proportion of 60 heads. So what is the probability of getting 60 out of 100 when we really expected 50 out of 100? Well, at this point, the probability would be 0.017, approximately 2%. So the probability of getting 60 out of 100 when we expected 50 is quite low. And then you can imagine if we did this all the way up to 600 times. So 600 out of 1,000 heads. So in this case, the probability of getting more than 600 when we flip this coin 1,000 times is approximately equal to something less than 0.0001, or very small. Now, what's changed? Well, in all three of these cases, the probability or proportion of heads to trials is 60%. In all three of these cases, the expected proportion is 50%. We expected half of them to be heads. But in the first case, we would say, oh, that's not too surprising. In the second case, we would start to question it because the probability of that happening would be very small. And in the third case, we would say, I want to see that coin. Well, what you're really saying here is that in the first two cases, this is just due to some random natural variation. But in the third case, we're so far out here on the tails that we have to say that it's not due to random or natural variation. It's really due to something other than natural variation. We would suspect that the coin is unequally weighted, or my method of flipping it is program or systematic, such that I'm getting, by design, more heads than tails. So this is my attempt to kind of explain what this p-value is. I think it helps that if you understand what the p-value is, that you can understand what it means when we say that it is statistically different, or we reject the null because the sample mean is statistically different than the expected mean.